Okay friends, today we will continue with the study of modeling of synchronous machine. Today we will address some of these issues: per unit system for rotor circuits, per unit power and torque, and alternative transformations. We have discussed DQO transformation, and we will also talk about the alternative transformation which has also been proposed in the literature, and then we will talk about the steady state analysis of the synchronous machine. Now, we have developed the per unit equations for the stator circuits. Okay. We have also developed actually the per unit equations for rotor circuits. Now, while developing these equations, we have defined these terms per unit LAFD, per unit LAKD. Similarly, the per unit LKQ. Now, these terms were defined and the definitions were given like this: LAFD bar equal to LAFD divided by LS base, IFD base divided by IS base. That is, these three terms were defined, but they are basically in the stator circuit equations. You see this, the stator circuit flux linkage equations, psi D, psi Q and psi O. Therefore, in these three equations we had defined these per unit inductances. Now, these per unit inductances are the mutual inductances. Okay. Similarly, when we talked about the per unit rotor flux linkage equations, we had defined these terms, these mutual terms LF, KD, LF, DA, these are all per unit quantities which were defined. Now we want to establish the per unit system for the rotor. Now, when I am trying to say per unit system for the rotor, in the sense that we have chosen the base quantities in the stator circuits. Now, how should we choose the base quantities for the rotor circuits? The rotor circuits are rotor field winding and rotor amortizers. Okay. Now, the primary consideration for choosing the base quantities in the rotor are to simplify the flux linkage equations, to make this flux linkage equation as simple as possible. Now, one requirement which we have put is, or one way of simplifying these, we make mutual inductances between different windings reciprocal. We make mutual inductances between different windings reciprocal. Now, when I say that we make these mutual inductances reciprocal, in the sense that there is a mutual inductance between the stator winding and the field winding. Okay. Now, if I write down the mutual inductance between the stator winding and field winding, I can write down LAFD. When I write down between field winding and stator winding, it can be written as LFDA. We want to make these two inductances equal, so that there is what is the meaning of reciprocal. Okay. Another thing which we would do to simplify the equations will be that the mutual inductances between stator and rotor circuits on each axis are to be equal. That is, when I say each axis, means we have two axes, D axis and Q axis. On the D axis we have the stator direct axis winding, field winding and amortizers on the D axis. Therefore, there exists mutual inductances between these windings. We would like to make them equal. Similarly, there exists mutual inductances between the Q axis winding on the stator and Qx is amortiguer. We want to make these mutual inductance also equal. Therefore, we are trying to do two things. One is that we will try to make, or we will make the mutual inductances reciprocal and the mutual inductances on each axis equal. Okay. Now, this will simplify the equations to a great extent. Now, how do we make the mutual inductances reciprocal? Now, to make the mutual inductance reciprocal, you just look at the, suppose you look actually this equation, I just put this is slightly, I have to make it I think LAKD. Okay. Now, this LAKD and another is LKDA, we want to make them equal. Okay. Now, these quantities were defined. Now, when to make them equal, reciprocal, okay. So, that what is to be done is that we equate the expression for this with the expression for LKDA. Okay. Now, we will start first that is, let us say that we want to make the per unit mutual inductance LFKD equal to per unit mutual inductance LKDF, right. That is the amortiguer and field winding. Okay. That is, these are the two mutual inductances, one between the field winding and amortiguer, another is between amortiguer and field winding, and we want to make this reciprocal. Now, these quantities were defined. Now, as per the definition, this quantity L bar FKD, that is the per unit mutual inductance between field and amortiguer windings, were defined like this, that is LFKD upon LFD base IKD base upon IFD base, that is in the denominator. Here is LFD base, IFD base, here you have LKD base, IKD base. Now, this is by definition which we have defined actually when we wrote the equations for flux linkage equations in the rotor circuit. Now, when we equate these two, okay, we will get this expression, that is just cross multiply, we will find that it becomes LKD base into IKD base square equal to LFD base IFD base square. You can just check it, it comes out to be like this. That is IKD base comes on this side. So, okay, and these two cancel out, they are equal. Okay, and we get this equation. Now, here what we do is we multiply both sides of this equation by omega base. Once you multiply by omega base, it becomes omega base into LKD base IKD base square. Similarly, omega base equal to LFD base into IFD base square. Now, you can identify this quantity omega L into I. This quantity, this is actually the voltage, this is a voltage. Therefore, I take this base frequency in radians per second, the base inductance, and multiply this by current, base current. This will come out to be base voltage. Okay. So, now we are taking these quantities for amortiguer, the quantities are for amortiguer LKD, IKD. Therefore, the base voltage will become the amortiguer circuit base voltage. This dx is amortiguer circuit base voltage. Similarly, here. Now, when you do this, you will find this very important relationship, that is the base voltage in the direct axis amortiguer circuit multiplied by the base current in the direct axis amortiguer circuit. This product must be equal to the base voltage in the field circuit into base current in the field circuit. This is very simple. That is the base VI in the amortiguer circuit should be equal to base VI in the field circuit. Now, if you do this, you will find actually that the mutual inductances, right, between the field winding and the amortiguer winding will become reciprocal. Okay. Therefore, this is one of important requirement, that base VA in the field circuit should be same as the base VA in the amortiguer circuit. Now, we do one similar exercise for mutual inductance between the stator winding, the stator direct axis winding and the field winding, that is stator and field, that is LAFD. We want to make this as LFDA, that we want to make these two per unit mutual inductances equal, right. Now, these quantities were again defined when we wrote the equations for flux linkages. Okay. Now, when we equate these two terms and follow the same procedure as we have done for the mutual inductance between field and amortiguer. Okay. Therefore, here again we come to very important result, and that result is that VI base, there is the EFD base into IFD base, that is the VI base in the field circuit comes out to be equal to 3-phase VA base for stator. Three-phase VA base for the stator. That in the stator circuit, when you assume that the base voltage as peak value of the phase voltage, the base current in the stator circuit is the peak value of the phase current, and we have established that this quantity is equal to 3 times VA, 3 times VA base for the stator. There is 3-phase VA base for the stator, the total volt ampere rating, right. Therefore, this is very important relationship, because in the we have also established the relationship that the base VA in the KD circuit, direct axis amortiguer, should be same as that in the field circuit. It means now we can conclude actually that these 3 windings, one in the field winding, another stator winding, third amortiguer winding, direct axis amortiguer winding. Now, if you want to make this mutual inductances reciprocal, then the volt ampere rating or volt ampere base in the stator circuit must be equal to the volt ampere base in the field circuit and volt ampere base in the amortiguer circuit, because in the stator the volt ampere base is equal to the 3-phase VA base, 3-phase VA total MVA rating. Okay. This is exactly similar to what we normally do. In any system, we take total 3-phase MVA as the base quantity, and then we talk about the base for the rotor circuits. We find actually that for rotor circuit, now if the field circuit we consider it, it has applied voltage V, EFD, and current flowing is IFD. Therefore, EFD base into IFD base becomes this product becomes the VA base for the field circuit. Therefore, this one condition we established, that if we want to make the mutual inductances between the circuits reciprocal, then this is the criteria required for choosing the VA base for this circuit. Okay. Now, the similar exercise have to be done for quadrature axis stator winding and the quadrature axis amortiguer, because so far we have talked about the D axis, and here also we establish the relationship, and that relationship is that EKQ base into IKQ base is equal to 3/2 ES base into IS base. Now, this quantity is nothing but the 3-phase VA base for the stator. Therefore, ultimately what is our conclusion? That all the circuits, all the circuits, that is all which are in the rotor, field circuit, amortiguer circuits, right, they should have their VA base equal to the 3 times or 3 phase VA base of the stator circuit. This is the, and this will make all the mutual inductances reciprocal. Therefore, now I conclude here that in order to satisfy the requirement that per unit mutual inductances between, again the emphasis is that we are trying to make the per unit mutual inductances reciprocal. Actual mutual inductances which exist, we have seen actually that they are not reciprocal. When you see the actual equations which you have written, right, they appear in the equations in a different fashion between different windings, reciprocal, okay, and the requirement is that VA base must be same and equal to the stator 3-phase VA base. This is the main conclusion. Okay. Now, the next requirement which we have posed here is that the mutual inductances on the same axis, we want to make them equal. First we made them reciprocal, and when the requirement was there, we want to make them equal. Now, to make them equal, we define the per unit self inductance of the D-axis winding, D-axis stator winding as leakage inductance, per unit leakage inductance plus per unit mutual inductance. That is, when you look at the D-axis winding on the stator, okay, the total per unit inductance is defined as LD bar. This bar stands for, or super bar stands for per unit. Now, the total flux which is produced, right, which links the D-axis winding does not pass through the field circuit or the amortizer circuits, D-axis amortizer circuit. There is some flux which is a local leakage flux. Therefore, this LL is accounts for the inductance of the D-axis stator winding due to leakage. Okay. Therefore, this becomes our mutual LAD bar. Similarly for Q axis. Now, here a requirement is that in order to make all per unit mutual inductances between stator and rotor circuits in the D-axis equal, that is, we have in the stator circuit a fictitious D-axis winding, okay, and the rotor circuit we have on the D-axis 2 windings, okay, and we want to make them equal. For making them equal, by definition, this is actual value of mutual inductance LAD divided by the LS base, okay, and this is equal to LAFD, which was earlier defined by this expression when we wrote the mutual or you can say when we write the expressions for the psi D, psi Q and psi naught, right. The LAFD was defined like this. Per unit value of LAFD was defined by this expression, that you can refer to the previous equations. Okay. Similarly, now we want to make LAD to equal to the per unit LAKD. Okay. While LAKD was defined by this expression. Okay. Now, what we meant that we equate these two as we did in the previous case, and when we equate these two, we come to one very important relationship, that the IFD base should be equal to LAD upon LAFD IS base. Similarly, IKD base comes out to be LAD upon LAKD divided by LS base. While these quantities are the actual inductances, actual mutual inductances, right? While what we are trying to make them equal are the per unit mutual inductances. Okay. Now, this gives a relationship that suppose I have chosen the stator base current, then the base current in the field circuit should be given by this equation. Similarly, if I chosen the base current in the stator as Is base, then the base current in the amortiguer circuit, direct axis amortiguer circuit, should be given by this expression. Okay. Similarly, you can do for Q axis also. That is, Q axis will give you that IKQ base should be equal to LAQ divided by LAKQ Is base. I hope you understand this. And this is straightforward. Okay. What we are trying to do is that what we want to make them equal. We want to make the per unit the mutual inductances on the same axis, d axis equal. That is right. We have to make LAD per unit equal to LAFD, which is the definition of LAD same as LAFD. We want to make this LAKD and LAFD equal. To make them equal, you equate these quantities which were the basic definitions for these per unit LAFD and per unit LAKD. Okay. And we finally get the relationship that the field currents, base value of the field current, base value of the amortiguer circuit current, and the base value of the quadrature axis amortiguer circuit current are expressed in terms of the stator circuit base current. Okay. Similarly, we had also established that VA base for all the rotor circuits in terms of the 3-phase VA base of the stator. And therefore, since actually when I talk about the VA, that the field voltage base into field voltage current base. Okay. Now, this product is equal to the 3-phase VA of the stator, right? But the individual currents will be defined by this expression. Now, once the current base is given for the circuits, we compute the voltage base for the rotor circuits using the previous relationship. I hope it is clear to all of you. Now, once we have done this and defined the model for the synchronous machine is complete. The synchronous machine model is complete. For our all further discussions, what we will do is that this super bar which we had put to identify these quantities as the per unit quantities, we will drop it. But we will always keep in our mind that these are per unit quantities. Once these are per unit quantities, because every time writing super bar is not very convenient. Okay. Now, further we can express the per unit power and torque. Per unit power and torque, in our previous derivations, the terminal power, total terminal real power was expressed as 3/2 ED ID EQ IQ plus 2 times UIU. Okay, that you can recollect. Now, here what you do is that you replace all these quantities by, that is, you divide by base 3-phase base VA of the stator here, that is, you divide this by base volt ampere, you divide all these quantities by the base voltage and currents. When you do this exercise, the power in per unit can be written as ED bar ID bar plus EQ bar IQ bar plus 2 times EO bar IO bar. Okay. There is only thing which happens is that this 3/2 term which appears in this expression disappears in the expression for per unit generator power. Okay. Other expressions are same except they are the per unit quantities. This exercise I will just suggest you to verify. You substitute the values and then verify that you get this 3/2 is. Then we obtain the per unit electrical torque or air gap torque, which will come out to be equal to per unit direct axis flux linkage psi d into IQ minus psi q into ID. In fact, this is the most important expression when we talk about the synchronous machine model. Why this expression is so important? Can you tell me? Other stator circuit, rotor circuit equations are also equally important, right? Because that gives the model, complete model. We have to write down the stator circuit equations, rotor circuit equations, stator circuit flux linkages, rotor circuit flux linkages, okay? And all these things have to be written in per unit by establishing proper per unit base. But when I say that the per unit air gap torque is given by this expression, then this is quite important. Can you tell me why? Yes.
Instead of calculating the torque in terms of 3 phase, we are getting the torque just by 2 values.
Now, because the torque is computed in per unit using the per unit flux linkages and per unit currents. This expression is going to be used in our swing equation. When we have written the swing equation, in the swing equation we have to write down mechanical torque minus electrical torque, and this is the electrical torque that will come in the swing equation. Okay. I will just mention briefly about alternative per unit systems and transformation. That is the DQO transformation which we discussed till now, and another form of DQO transformation which has been discussed in the literature and also used by some people. Here in this, the DQO quantities are expressed in terms of this transformation matrix into the phase currents, that is the phase variables IA, IB and IC. Now, if you see this transformation matrix, the main difference here is that the DQO transformation which we use, right, this quantity or this term KD, this is a KD, was a KD or KQ, they were both taken equal to 2 by 3. Here they are taken as square root of 2 by 3, and correspondingly the last row, that is the third row, the terms become, instead of 1 by 2, it becomes square root of 1 by 2 and so on. Now, with this transformation, if you write the inverse transformation, that is you write down the phase currents IA, IB and IC in terms of DQO quantities, right, then this becomes the inverse of our transformation matrix. This is the transformation matrix we use. Therefore, if you invert this matrix, right, then we can write down using this inverted matrix the relationship between the phase currents IA, IB and IC in terms of DQO components. This inverse, if you just see here, then this inverse is nothing but the transpose of the transformation matrix. You can just see here actually that this row is the column here, right, while this row appears as column in the inverse, okay, and therefore this is the inverse of the transformation matrix, but it is also the transpose of the transformation matrix. Now, whenever you have this type of situation, we call this transformation as orthogonal transformation. Now, when you resort to this transformation, one very important result which we get is like this: the terminal power PT, right, which when we write down as EA into IA plus EB into IB plus EC into IC. This is a terminal, okay, This PT is average or instantaneous? Instantaneous. But what is average? Huh? The average and instantaneous become equal. In a three-phase system, the total power is total or the average power is constant. Not what instantaneous power we calculate. This sum will come out to be equal to average power. Right. Therefore, now if you substitute here, that is you write this equation, that is this equation can be written as PT can be written as EA, EB, EC multiplied by IA, IB, IC. Is it not? This expression is written, you can put in the matrix form. This row vector multiplied by this column vector. This will give you EA, IA plus EB, IE plus EIC. Now you replace this row vector by DQ components. You replace this also by DQ components and multiply these two matrices. When you do this multiplication, the end result comes out to be of this form. That is, the PT will come out to be equal to ED ID plus EQ IQ plus EO. It is something like this, that when I had 3 voltages and 3 currents, okay, I got the terminal power by multiplying these quantities. Similarly, I have now the direct axis voltage, quadratic axis voltage and 0 sequence voltage. Similarly, the direct axis current, quadratic axis current and 0 sequence current. I multiply and add. This comes out to be equal to, right. Now, for this type of, therefore, this transformation is called power invariant transformation. Power invariant transformation, and it has some merits which has been discussed in literature, but it has some demerits also, and that is why in most of the models which have been developed, the DQ transformation which was discussed earlier is used, where we use KD and KQ equal to 2 by 3. Okay. Having developed the synchronous machine model, we have developed the synchronous machine model completely in using per unit quantities, and the model is developed in DQO frame of reference. Okay. Now, this model is the complete model, and now what we will study from this point onwards will be, first we will study the steady state aspect, okay, and then we will go how this model can be simplified for our stability studies. Okay. That is, this is the complete model actually, right, but sometimes we can make some assumptions and simplify the model. Okay. And how do we simplify this model which will be suitable for stability studies? That is what we will study in the subsequent lectures. Now, let us quickly do the steady state analysis, because steady state analysis is one which is known to everybody. All of you know this analysis, but now we will develop the steady state equations for the machine, starting from our dynamic model of the synchronous machine. Okay. Now, when we talk about steady state conditions, we are presuming that the synchronous machine is operating under steady state condition, and the stator currents and voltages are balanced 3-phase currents and voltages. That is, this is with the assumption that it is a steady state operating condition, and the stator and stator quantity, stator currents as well as the stator voltages are balanced. With this assumption, once it is steady state, this derivative terms will be absent. In the steady state condition, we do not have anything like d by dt of psi. Suppose I take it, psi will be a constant, therefore the derivative term will be absent. Second is that all zero sequence terms will also be absent, because it is a balanced 3-phase system. Okay. With this assumption, the stator circuit equations can be written now in per unit. Again, remember that these are all per unit stator circuit equations. The bar is not written here, while the stator circuit equations are written in the form E d equal to minus omega r psi q minus r a I d, E q equal to omega r psi d minus r a I d, and E f d equal to r f d I f d. It is very simple actually. You can just, in all the three equations, the p psi d terms have been, p psi terms, that is the derivative terms have been set equal to 0. Okay. Now, under steady state operating condition, the rotor speed is equal to synchronous speed. Therefore, we substitute here omega r equal to omega s, and in the per unit system we will see that omega r is equal to omega s equal to 1. Okay. Now, these are the three voltage equations, these two voltage equations for the stator circuit, this voltage equation for the field winding, and these are the flux linkage equations, that is psi d and psi q in per unit quantities, they are all per unit terms. We have not done anything except that in these equations the derivative terms have been set equal to 0, right. Another thing, while writing here, we have also said the mutual inductances, per unit mutual inductances on the d axis windings are equal, right. Therefore, you will find here actually, when you write down this side is L A D I F D, when you write down psi f d, again I have put L A D, because the mutual inductance between the stator d axis winding and the field winding have been made equal in per unit system. Okay. Therefore, this simply appear as LAD. Okay. Further, actually, when you have written these equations, suppose there is one amortizer on the d axis, k becomes 1 here. Suppose you take one or two amortizers on the q axis, one equation will be for psi 1 q. If the second amortizer, it will be psi 2 q, right, and they will be written in the by the same equation minus LAQ IQ. Why this same LAQ will come? Because mutual inductances between the two amortizers on the q axis, when expressed in per unit, are equal. Therefore, this. Okay. Now, here we can just derive one simple expression for field current. What we do is that in these equations, just start with this. Suppose you take, because my interest is to write down what will be the value of field current required or field current in per unit required to produce the required steady state operating condition. So, that using this expression, you can write down the expression for IFD, that is IFD is written first here as psi d plus LD ID divided by LAD, and then this psi d, that is a per unit flux linkages in the d axis, will be replaced by this equation psi d equal to minus LD ID, not here actually this psi d, because we will resort back to our stator winding equations, that is psi d can be written using this equation. Okay, that is EQ equal to omega r psi d minus R A IQ. Okay. And when you make these substitutions here, we get very important relationship. is this relationship, that is the field current which is required to produce certain value of EQ, the IQ, ID with these quantities known, they are all the machine parameters. Now, per unit stator resistance, per unit direct axis inductance, per unit mutual inductance between direct axis and the field winding, these are all now circuit parameters or synchronous machine parameters, they are all known. Okay? And therefore, when system is operating with some load, that load will determine IQ and ID. Okay? And to have then for a particular value of EQ, this is the value of IFD required. Therefore, for all our studies actually, as we will see further when we talk about the models of the synchronous machine, for our stability studies, this information is required. But this is simply obtained using those equations, that is the stator circuit equations, flux linkage equations, and making some appropriate substitutions. Now, we use this omega r is equal to omega s, and this omega s into LD will represent by XD. Omega s into LD will be represented by XD, right. Similarly, you can say omega s into LAD will represent by XAD, reactance. Omega L is equal to reactance always. Okay. Therefore, in this equation is written exactly the same, but instead of writing in terms of the per unit d axis inductance and mutual inductance, it is written in terms of XD and XAD. XD is the direct axis reactance, while XAD is the mutual reactance between the field and the d axis winding. Now, we will quickly see now the phasor representation. Before we talk about the phasor representation, let us restate some of the facts. Under steady state conditions, the ID, IQ, these two currents are constant in magnitude. Therefore, basically the current flowing in the fictitious d axis winding and the fictitious q axis winding are DC currents, direct currents. Similarly, the ED and EQ came out to be constant voltages that we have already established under steady state operating conditions. Now, the question arises is that when we draw phasor diagram, right, all the phasors are corresponding to a sinusoidally varying quantity, that is all the quantities which vary sinusoidally and having the same frequency, right, can be represented in the phasor diagram. Okay. But here also, although these quantities are constant in magnitude, because of certain trigonometrical relationships which exist, we will be in a position to represent these D and Q axis voltage and currents as phasors, but with a clear understanding in our mind that D and Q axis quantities are scalars. ED, EQ, ID, IQ, they are scalars, right. But because there exist trigonometrical relationships between the certain phasors and the D and Q axis components, therefore, we can represent these quantities in the phasor diagram. Now, to start with, let us say that we have a balanced steady state operation. The phase voltages are given by these equations. Okay. That is E A is equal to Em cos omega st plus alpha. Alpha is some arbitrary angle, a reference angle where you start with, and this Eb is lagging by 2 pi by 3, 120 degrees, Ec by leading by 2 pi by 3. Now, you apply dQo transformation to this equation. When you apply the dQo transformation, you will get the d axis component ED and q axis component EQ as EM cos omega st plus alpha minus theta, EM sin omega st plus alpha minus theta. That is, in fact, when you apply this transformation, right, to arrive at this result, we have to make use of many trigonometrical identities. That is, when you put these equations, right, A, E, B, and C, this column vector in the transformation matrix, you will find actually that these trigonometrical terms will have to be multiplied with the elements of that matrix, transformation matrix, and finally to come to this result you may have to use number of trigonometrical identities, okay, and the final result is going to be in this form. Okay. Now, we can represent the angular position theta as omega r into t plus theta o, and omega r is same as omega s, because it is a steady state operating condition. Now, when you make this substitution, ED comes out to be equal to EM cos alpha minus theta o, EQ comes out to be equal to EM sin alpha minus, okay. And therefore, in this equation, when we find here in this equation, there is no term like omega st, right, and therefore, ED is constant, it depends upon the peak value of the stator phase voltage and the alpha and theta naught. Okay. That is why I said that this ED and EQ come out to be scalar quantities under steady state operating conditions. Now, ED and EM, suppose the ED is d axis voltage and is in per unit. Okay. Now, we are more comfortable when we use the RMS value of the voltage rather than using the peak value of the voltage. Now, suppose I assume the peak value of the stator voltage as my stator base voltage, then RMS value of the stator base voltage, when it is expressed in per unit, will come out to be same as the peak value. It is something like this, that I have chosen the base voltage in the stator circuit, and that base voltage is peak value of the per unit of the phase to neutral voltage. Okay. Now, if I want to express any quantity in terms of this, then they are expressed in terms of the peak value. Now, if suppose I have chosen the stator base voltage as peak voltage, I want to choose the base voltage in terms of RMS value, then it is automatically going to be the base voltage, which is the peak value, divided by root 2. And therefore, if you express these quantities, that is ED and EQ, not in terms of peak values, but in terms of RMS value, the equation will remain same, because the base values of the stator voltage, when it is expressed as in terms of peak or when it is expressed in terms of RMS value, they will have a relationship of 1 by root 2. Suppose I take the stator base as 100 volts, then this is a peak value. Then RMS value, RMS base value will be equal to 100 by root 2, and therefore, this equation can be written in terms of the RMS value. Now, I put ET as the RMS value, and it remains same, there is absolutely no change. This is also per unit, this is also per unit. Okay. Now, when we represent these quantities in the phasor diagram, it will look like this. Let us say this is the terminal voltage phasor. I represent this ET tilde, putting this as a phasor quantity, because we used bar earlier, super bar earlier for representing the bar per unit quantities. Okay. That is why we are putting ET tilde. And let us show that this is my d axis, this is the q axis leads d axis by 90 degrees, and here the angle is alpha minus theta, because we have seen here actually that the angle comes out to alpha minus theta o, right. Then ED is represented by ET cosine alpha minus theta o, and EQ is equal to ET sine alpha minus theta o. Therefore, this phasor diagram is expressing these quantities ED EQ in terms of ET. Similarly, you can draw a phasor diagram showing the currents. Let us say this is my terminal voltage phasor. So, this is the current phasor, and let us say that phase difference between the voltage and current is phi, right. Then we can express the d and q axis components of current as ET, I am sorry, current can be expressed as ID equal to IT sin delta I plus phi, IQ is equal to IT cos delta I plus phi. This exercise is done similarly to what we did for voltages, right. Therefore, in the phasor diagram I can simply show IT equal to ID plus J times IQ, okay, and this diagram I have just now shown to you. Okay. Now, here the angle between the q axis and the terminal voltage will denote by delta I. Okay. Now, one small exercise which is an important exercise to be done is to establish the position of d and q axis with respect to the terminal voltage. That is, I know the terminal voltage, and with this terminal voltage as phasor I have to establish what is the position of q axis, what is the position of, that is, if I establish the position of q axis I can automatically get the position of d axis. Now, to establish this, now some of these equations are all repeated, you know, the ED is given by this expression we already established. To establish the relationship, what we do here is we define a voltage EQ, a phasor EQ as terminal voltage plus RA plus J times XQ into IT. This is this relationship is a very well known to all of us, right. That is just start like this, that my intention is to establish relationship between the terminal voltage and the d and q axis. We define a voltage EQ as ET plus this impedance RA plus J times XQ into IT. With this definition, and we substitute the expression for ED, ET as ED plus J times EQ and IT as ID plus J times IQ, and we make simplifications. That is, you multiply and simplify this expression, you will find that EQ comes out to be J times XAD IFD minus XD minus XQ ID. What does we get from this equation? What this equation conveys to us? This equation conveys that this voltage EQ which I have assumed, right, is in quadrature with d axis. This is along q axis, not it is of course quadrature with d axis, but it is along q axis, because our reference, with reference to the reference, this quantity is ahead by 90 degrees, that is j term is existing, because the other terms are all scalars. Here actually the terms are all scalars. Okay. And therefore, the phasor diagram which I draw here showing this ET plus RA IT plus XQ IT, this gives a voltage EQ. That is, with respect to this terminal voltage ET, the position of EQ comes out to be along q axis, right. And therefore, we have now established the relationship between the terminal voltage and q axis, and once we establish relationship, d axis position is known, and all further computations can be done the moment we know the d, q and other quantities. Friends, I will conclude my presentation here by summarizing what we have done in this lecture. First thing, that we have established the base volt amperes for the rotor circuit. We have also established the how to choose the base current for the rotor circuits in order to make the mutual inductances reciprocal, and also to make the mutual inductances on d axis and mutual inductances on q axis equal. Okay. Then we have also established the steady state relations and developed a simple phasor diagram to show that the q axis can be obtained by obtaining the position of a phasor which is equal to terminal voltage plus an impedance equal to R A plus j times x q multiplied by the current. That is, if you compute this quantity E q equal to terminal voltage plus impedance, that is R A plus j times x q multiplied by the current. This gives me the position of q axis. Okay. Thank you.